Yeah.
Performance this evening. He's been resoundingly.
Bismillahirrahmanirrahim. Assalamualaikum. Good morning, everyone. Can you hear me?
Yes, Doctor.
Boleh, Dokter.
Right. We move to the slide number 94. Okay. PID controller. Okay. So PID stands for Proportional Integral Derivative Controller. Okay. And it apply in a lot of industry. Okay. In energy industry, in transport in agencies, okay, semiconductor company and so on. Okay, so actually it is a worldwide controller applied in industry. It can be in digital form. Okay, so this is a digital form. You just key in the KP, KI, and KD value. Or you don't have budget, so you use a small Arduino Uno or Raspberry Pi controller. Okay, write the program and then set the value of KP, KI, and KD view using several tuning method. Okay, this is actually the block diagram of the proportional integral and derivative controller. So we learned previously that P controller have a drawback, disadvantage, that is it produce steady state error. Then we come out with the solution to solve the steady state error respond by introducing a PI controller. Then we solve the steady state error, but it takes a long time for the system to achieve zero steady state error. So the slow response give a drawback or disadvantage of PI controller. So therefore, we introduced PD controller last 2 days in the Monday's lecture. So it seems that PD controller solve the issue of the transient response improvement from slower response to faster response. So if we want the system to have a zero steady state error and at the same time have a good transient response, a faster transient response. So we have to use both together in one controller. So that's why we use PI and PD. We combine together, it become PID controller. That is to improve the steady state error from finite value to zeros and improve transient response independently, meaning that it improves from slower response to fast response. Both are simultaneously, okay, done in one controller. So we call it as a PID controller, since it's a combination of PI and PD controller. So how to design so that the transient response and the zero steady state error achieved? So we look at the transfer function here where GPID is equal to Kp plus Ki over S plus Kds. So this is term for the proportional, this is the term for the integral, and this one is the form of the derivatives. So when we combine together, we multiply together, so we will get kps plus ki plus kds square over s. Then we simplify by factorize, okay, kd become the common factor multiplied by s square plus kp over kd plus ki over kd. So this one we can see that as the z1 and this one is the z2, which is the ratio. Okay, the ratio for the system. So that's why it becomes GPID is equal to KS plus Z1 over S and S plus Z2. Right, so the implementation of PID controller is based on the two zeros and one pole at the origin. Okay, so if we look at the S-plane, so it will be somewhere here, poles and zeros at the origin. Okay, it can be like this. Okay, so the block diagram usually we refer here K1 for the proportional, K2 over S for the integral, K3S for the derivative. So is highlight in the dotted red line, that is for the controller. Okay, and then it will be cascaded to the system with the transfer function or the model, and then unity feedback for the closed loop purpose. So we see example 6 here, okay, where you are given the system, you are required to design a PID controller so that the system can operate with the peak time that is 2/3 of the uncompensated system at 20% overshoot and zero steady state error. What do you mean by that? So example 6, where the spec design is settling time or peak time? Peak time. Peak time new is 2/3 of the old peak time. Okay, that is spec number 1. Spec number 2 is 20% overshoot. This will give you zeta value, and then zero steady state error for step input. So your controller must fulfill these 3 desired, okay, or spec design. Okay, so let's start by looking at the mathematical model. So this is the model. Okay, so from the model, it is a third order system. Okay, system type is equal to 0. Open loop poles, open loop zeros is -8, and open loop poles is -3, -6, and -10. Okay, so we determine the open loop transfer function directly from the given model. Okay, ks plus 8 s cubic 19s square 108s plus 180, and the closed loop transfer function, and the denominator of the closed loop transfer function is the characteristic equations. Okay, So the plot is shown here, where you have -3 poles, -6 poles, and -10. And of course, there is zeros at -8. Okay. So it have this is open loop poles have 3. So that's why the branch of root locus is 3. Okay. You have this one, the red one, the green one, and the blue one. Okay. So all the arrows start from the poles, then ended at infinity positive, and ended at negative infinity. And this one is start from -10 and ended at -8. 3 root locus branch. Okay. Then by the given 20% overshoot, by using a graph of this graph, okay. So 20% is about here. So it gives you 0.456 zeta values, okay. So use this one, So no need to use the formula because it will make you slower in the calculations. Time is very limited, so you use attachment graph. 0.456 is the zeta values. For zeta 0.456, so theta is cos inverse, which is equal to 62.87 degrees. Okay, which is here the theta, and this is the origin. So -3, -6, -8, and -10. Okay. And this is the dominant pole, the correspondent dominant pole. Okay. Akmal Hakimi, can you give me the dominant pole over there?
Negative 5.42 plus J 10.6.
10.6. Okay. And then the third pole, Akmal Hakimi,
Negative 8.16.
8.1. Okay. So the K value over here is 122. The K value. Okay. So using the magnitude formula, you will get 122. So this is the dominant pole, guys. As Hakimi said just now. And the whole peak time is calculated by pi over omega d, or pi over modulus imaginary part. So imaginary part is this one. So 10.6, 3.414 divided by 10.6, you get 0.296 second. And then for the new peak time, as I told you before, in the spec design is 2/3 of the whole peak time. So this one is 2/3 multiplied by 0.296 second. So you will get 0.197. And it is equal to pi over omega n square root 1 minus zeta square. So zeta we calculate just now is 0.456. So that you calculate the omega n new, okay, which is 18.54 radian per second. Okay. Then you get the new dominant poles, which is the real part is -8.17, and the imaginary part is J16.54. So this is the new. Okay. new dominant pole. Okay. So you use this pole, the new dominant pole, as the test point over here to calculate the angle for the PD controller. Okay. That is known as minus Z. We assume the locations of the zeros of the PD controller at minus Z with the corresponding angle theta phi. Then angle of poles minus 3 or minus 10 theta 3. Angle for zeros of minus 8 is theta 4. Angle for the poles at minus 6 is theta 2. And finally, angle of the poles at minus 3 is theta 1. So we calculate using the angle criteria, which is this one. Okay. Theta 1 plus theta 2 plus theta 3. These three poles, this angle actually from the three poles, then minus theta 4 from the zeros minus 8, and minus theta phi from the zeros of the PD controller. Okay, so calculate the corresponding angle alpha 1, alpha 2, theta 3, alpha 4. Then you get theta 5 is about 19.88 over here. So calculate the angle, the x, okay, at theta 5, which is equal to minus 54.21. Okay, so the location of the zeros is minus 54.21, which is minus 8.47, the real part of the new dominant poles, plus minus 45.74 from the x value. So completed, and then we calculate the gain as here. This one is using Pythagoras theorem, but you don't have to do that. You assume this one as S. Then you insert inside the K value, which is S plus 3, S plus 6, S plus 10 over S plus 8 and S plus 54.21. Okay, so we take this value, the new dominant poles, as S, insert inside this K using calculator, then simplify, you will get the value which is equal to 6. Okay, guys, two ways using L1, L2, L3, which is I'm not advised. Okay, so you use this one is much better. Okay, easy to calculate. So is it we need to redraw the original root locus? No need. Okay, no need because now the new peak time is 0.297, new dominant pole here, and the angle of 0 is about 19 degrees. Okay. So now the transient already improved. Okay. Already improved from 0.296 second to 0.197. It's already improved. Okay. From slow response 0.296 second to fast response 0.197. Now our focus is to make the steady state error become 0 by introducing this PI controller. Okay, so this sample is taken from the Norman Nice book. So it proposed 0.5. Okay, also can be usually I teach 0.1 or 0.01 or 0.001. Okay, I think it should be no problem if you want to choose 0.1 also can, or you want to choose 0.01 over S also can. Okay, so because this one automatically when you cascade it with the overall transfer function with PD controller and the system, it increase the system type from system type 0 becomes system type 1, meaning that it will make the system, it will force the system steady state error from finite value to zero value. So what I did is I multiply. This one is the PD controller. This one is the PI controller. So and the gain key. Then I multiplied using the gain key that we get, which is the 4.6. And then we multiply, this is the final PID controller, okay, which is S square plus 56.42 S plus 27.96 over S. So we calculate the value of KD, KP, and KI by using comparison between the what you obtain in your calculation and the standard PID controller. So you compare. Okay, from the comparison, automatically KD is 4.6. Okay, 4.6, then KP over KD, which is the second terms, which is 56.42. So KP is equal to 259 over 5. And then the third one is 27.96. You compare with KI over KD, and KI is equal to 128 over 62. So this KP, KI, and KD value will be inserted inside the controller hardware. If you are using hardware, so you use to tune the variable resistor, okay, like this, okay, output, input voltage, and then ground. So you adjust this one, okay, from minimum to maximum to achieve 4.6, 259, and 128. Or simply, if you are using the digital controller, you just key in the number. This number 4.6, 259, and 128. Because this number has been calculated, has been simulated by you as the control engineer. Then we test the time response, which is a before controller, uncompensated. We call it as uncompensated or before controller. And you can see that the input is 1 volt. Okay. Then we have a problem here, which is the steady state error. Okay. So what is the value of steady state error over here? Yong? Yong tak datang.
Ya, Dokter.
What is the steady state over here?
1 minus 0.8, 0.844
Which is equal to
equal to 0.156.
Thank you. Second. Sichai, Zin. Sichai, Zin. Sichai, Zin. Hello.
Yes, doctor.
What is the settling time? Given
0.7.
0.7 seconds. Aulia, what is the peak time?
1.02.
1.02. Astaghfirullahalazim.
0.6.
Huh?
0.6.
0.6. Peak time.
3.
Here, peak time.
0.3.
0.3. Okay. 0.3. What is the Cmax? Maximum amplitude? GN?
1.
GN?
1.02
Due to what? RM, Sing dollar, unit?
radian per,
1.0. 1.0.
radian per second.
Astaghfirullah. Amplitude is not radian per second. That is a frequency. C max, maximum amplitude here is a voltage 1.02 volt. Okay. Then we get the time response after PID controller after compensated. Okay. So after compensated, what is the steady state error? Dylan? Datang. Pak Izin, what is the steady state error?
Steady state error is wait, the no, zero at the last zero
Huh?
at the very last is zero.
What is the settling time, Pak Izin?
Settling time is 0.1 no 0.198.
Settling time.
Oh, 7 seconds. Wait, no.
Oh,
2.56.
wah. 2 point.
56. Sorry.
Peak time, Pak Izin?
Peak time is 0.196.
New, The old one,
The old is
0.3.
0.3.
So the ratio, Pak Izin, ratio.
Ratio 196 over 0.3.
Apa?
0. Oh, terbalik. Sorry. 1.53.
Huh? 0.3
1.53.
divided by 0.19. 0.3 divided by 0.19.
0.19.
Uh,
1.58.
1.58.
58.
Okay, it's about two-third lah. Okay, two-third.
Doctor,
Yes.
what is settling time before PID controller?
What is
Settling time before PID controller
before 0.7?
and after 2.9. So you said like we want the response to be faster. It's longer time.
No, settling time is not our concern. Our concern is peak time, brother. The
Okay.
spec design, we are not emphasis on the settling time. We emphasis on the peak time.
Okay. شكرا.
Okay. But you can see that the peak time has been reduced, okay, from 0.3 to 0.2. Okay. Right. So this is the comparison, three graph in one. The first graph, this one is the uncompensated, okay, before PID controller design, okay. Then the light blue is the PD controller, okay, still have error. And the final one is the PID, okay, where it solve the problem, solve the steady state error, become 0, and then peak time is two-third, okay, from the previous one. This is the way we get the value of Kp, Ki, and Kd. There is another way to get this value. We call it as a tuning method. Okay, tuning of PID controller. So there are several methods for tuning a PID controller. So you can Google many methods. Okay. So the PID controller is widely used in the industry, which the KP, KI, and KD are the parameters that easily being adjusted. Okay. So if you are using hardware, of course, you use the potentiometer to set the KP. So you have three potentiometer. One potentiometer for KP, one potentiometer for KI, and one potentiometer for KD. Okay, you have three times, three objects. Then you tune, okay, generally involve the choosing of the right values, the right parameters values of KP, KI, and KD. And this is depend on whether the control loop can be taken offline or online on the response time needed of the system. Okay, so online meaning the system is ongoing. Okay, when the motor rotated, so you tune over there to get the KP, KI, and KD. That one we call it as online. The other one is you just take the data, you off the system, then you analyze. So this one is offline. The system is not ongoing. Okay. So we have several methods here. Okay. Choice of tuning method. One is using a manual tuning method. No math required. Okay. Is online. Disadvantage is it requires experienced personnel. Okay, very experienced person that know the behavior and the characteristic of the system. The second one is using a Ziegler-Nichols method, which is a proven method. Can be applied online. It can sometimes upset the process. Some trial and error needed, and it is a very aggressive tuning. Okay. The other one is using software tools. Okay, so software tools need consistent tuning. Online and offline can be applied, and you can use various technique method. And some cost of the training involved in these software tools, license, training for trainers, and so on. And the other method is Cohen Cone, also for process model. Okay, it's a lot of model. Okay, so we only focus for this one, for this subject, Ziegler-Nichols method. So the following of the table summarize the effect. When
Jadi kau ni memang membuat internet slow.
Kenapa? Kenapa? Kenapa tu? So the effect of increasing parameter independently, okay, we have KP, KI, and KD. So when we adjust KP, the rise time will decrease. Small change in settling time, increase the overshoot, decrease the steady state error, and degrade the stability. While when using KI, it decrease the rise time. You adjust KI, increase the settling time, increase the overshoot, eliminate steady state error, which is become zero, and degrade stability. But for KD, when you adjust KD, some minor change of the rise time, decrease the settling time, okay, decrease the overshoot, and there is no info on the effect on steady state error, and stability will be improved provided using a small KD. So this method is used when the system models cannot or difficult to obtain either in the form of differential equation or transfer function. When we should use Ziegler-Nichols method, when the system models cannot or difficult to be obtained, either in the form of differential equations or in the transfer function. So Ziegler-Nichols introduced an effective method for the parameters adjustment using the ultimate cycle method. Okay, the method that run Ziegler-Nichols method, we call it as the ultimate cycle method. And this ultimate cycle method have a steps as follow. which is first you set the KD and KI equal to 0 first to minimize the effect of derivation and integration. Make it 0 first. Then increase the proportional gain, KP, until the system reach the critical stable, okay, when the root locus intersect with the imaginary axis, okay, critical stable. K crit, we call it as the K critical, okay, that is using Roth-Lewis or observe from the given plot. And at this point, where the gain is critical, the oscillation, the response of the time response is oscillate. Okay, as I show you in the class. Okay, it's oscillate. Okay. When the closed loop poles located at the imaginary axis. So obtain the gain K, gain critical gain, which is Ku, and the oscillation frequency, which is omega U, in radian per second or in period Tu on that particular time. Then calculate the Kp gain that is supposedly needed using a formula in the table. So based on the type of controller, calculate the necessary gain using formulas in the table. So these Ziegler-Nichols must use a table. The table is attached in the test or final exam. So this is the table. Okay, so you use the last one, PID here. Okay, 0.6 KU, TU over 2, and TU over 8. Okay, KU actually is the K critical. Okay, and the omega D is actually the omega U equal to omega U. Omega U is equal to, we'll talk this one later. Okay, so TU is equal to 2 pi divided by omega U. Okay, so once you know omega U, you already know 2 pi. So 2 pi divided by omega U, then you will get TU. So TU over 2 for TI integral and TU over 8 for derivatives. Okay. Use the third one. This one no need. Okay. Then compare with the standard GPID transfer function for PID controller, which is shown here. And from there, you can know what is the value of KD, KP, and KI. Example 7. Irfan Hakimi,
Ya, Doktor.
tolong baca.
Example 7. Design a PID controller for unity feedback system with open loop system, which is given as JS equal to K300 divided by S squared plus 30S plus 100.
Thank you. So, Irfan Hakimi, this is system order berapa?
System order, second order.
Astaghfirullah.
Tak order. Sorry, tak order.
Kau ni mimpi ke? Sekejap. Dalam. So this one is 300K over S cubic plus 30S square plus 100S. Okay, so third order, guys. Irfan Hakimi, what is the system type?
System type System type 1.
Tak dengar. System type Irfan Hakimi.
1.
Lambat. What is the closed loop transfer function Irfan Hakimi?
K3 300 divided by S cubed plus 30S squared plus 100S plus K300.
And lastly, what is the characteristic equation, Irfan?
S cubed plus 30S plus 100S plus 300K equal to 0.
Good. Okay. So we plot the root locus. So we have open loop poles at 0. Ni berapa Berapa ni? Irfan Hakimi, can you find the roots for this? Roots using calculator.
Negative 15
Yeah.
plus
Roots
negative 3.82.
negative.
3.82.
Okay. And
And negative 26.18.
negative 3.82. Correct.
Yes.
Okay. The open loop poles. Okay. So we have one breakaway point over there. Okay. So the time response without controller, without PID controller, without controller, uncompensated, okay? Share Sharon Lau. Sharon Lau.
Hello?
Steady state error.
0?
Okay, 0. 1 minus 1, Settling time, Sharon.
2.45.
Peak time.
1.11 second.
Okay. So it seems that the system is type 1. So the steady state error is 0. Okay, so we need to tune such that we get the fast response. So solution. So this is a solution. First we assume KI and KD equal to 0. Okay. Then we find the open loop transfer function, then we find the closed loop transfer function, and we find the characteristic equation as said by Irfan Hakimi just now. Okay, so we insert this one, the characteristic equation 1, 30, 100, and 300 kp. So side by side, this one is a 0. Okay, and continue with the fill up. Okay, this one and this one. Okay, because we are going to find the K critical, which is KU, and omega critical, which is omega U. Okay, so what we do is the first column of the Roth width is greater than 0 for stability. 1 is greater than 0, 30 is greater than 0. 100 minus 10 kp is greater than 0. Simplify. Okay. So we simplified. Then kp is equal less than 10. The second one is 300 kp is greater than 0. So kp greater than 0. So the final range of stability is range of k for stability is between 0 and 10. Okay. Farina Jaslin. Farina
Yeah,
Farina,
yeah,
what happened if Kp is equal to 11?
unstable,
But Farina again, when Kp is equal to 1, what happened?
stable,
When Kp is equal to 10, what happened?
stable, marginally stable.
Ordinary stable or critical. Okay. So therefore, we choose Kp is equal to 10. Okay. Which is this one. And we insert inside the even equations. Even equation is from the Routh-Weiss. Ruth, who is stable, which is over here, guys. Even equation. Okay, S square. So 30s square plus 300 kp equal to 0. Insert kp is equal to 10. Simplified, then you get omega, which is equal to 10 radian per second, guys. 10 radian per second. Then step number 4 is to find Tu. So Tu is omega is equal to 2 pi f, which is equal to 2 pi Tu. Okay, guys, 2 pi Tu equal to 10. Then manipulate equation Tu, so you will get 0.6283 second. Okay. After that, you use the table here to find Kp. Okay, Kp is 0.6 Ku. This one, which is equal to 6, guys. Then find Ti. Ti is Tu over 2. So Tu is 0.6283 divided by 2, 0.3141 for Ti. And then Td is Tu divided by 8, 0.6283 divided by 8, which is 0.0785. Okay. And then calculate this one, Ki, okay, which is equal to Kp divided by Ti and Kp divided by Td. So you get 19.1 for Ki and Kd 0.47. Then you insert inside the equations here. And finally, you get the controller, the GPID controller. Okay. Second example is about the same. Okay, using same example. This one is a third order system. And type 1. Okay. So same method. Okay. Step 1, step 2. Then use a row twist. Look at the first column. Okay. Greater than 0. And then from the root width, we obtain the value of Kp. The range is here. So K critical is Kp is equal to 12, which is equal to Ku as well. Okay. Insert the values, the square root 3 radian per second. Okay. What is the Izzah Shamimi? Square root 3 itu berapa? Square root 3. 1 point.
1.732
radian.
per second.
Okay. So it's inside 1.732. Then TU is 3.26. And as usual, KP, TITD, use the table, and then KI and KD is shown, then put inside the value. So you will get the KP, KI, and KD transfer function. And the last one, Cohen tuning method, ignore, no need to study, okay, as told by the coordinator. So you can ignore this one, okay. It's not included in the test, it's not included in the final exam as well. Okay, ignore. Because we have a new chapter. Okay, so this one is Cohen, no need as well. No need. Okay, no need. Then the conclusions. So we already covered for the time domain, proportional controller, PI controller, PD controller, PID controller, and tuning method PID controller using Ziegler-Nichols method. So this is the end for chapter 2. Okay, for next week, we will do some revisions. Continue for revision test 1, which will be held on the 13th of November. Thursday, okay? So class on the 11th and 13th will be revisions. Okay, guys? Everybody okay?
Okay, Doktor.
Okay, so I will share the video later. Okay, so kindly watch, view, and like. Okay. Is there any questions before we dismiss? No question?
What about the attendance, Doktor?
Oh yeah, attendance. Thank you for your reminder. So let me generate first the attendance. Wait, Okay, section 1. Section 1, guys. Stand by. Section 1 first. Okay, section 2, wait. Okay, section 2 now. Okay. So if there is no question, thank you very much for your attentions. Okay. See you again face to face next week, guys. Water supply now is 100% okay. Okay, so see you next week. Okay, guys, goodbye.
Alright,
Okay,
Doctor.
Thank you,
Doktor.
Doktor. Assalamualaikum.
Salam.
Terima kasih, Doktor.
Bye.
Thank you, Doctor.
Bye.